In this week's lesson, we're going to talk about the sun and how the sun has evolved over time. Everything that happens with the climate, with the weather, is related to the sun. The sun is the source of all the energy on the planet, and therefore we have to know something about the sun before we continue talking about the climate. So let's talk about some of the facts about the sun. First of all, the mass of the sun. So here you can see that the mass of the sun is approximately 2 times 10 to the 30 kilograms. That's 2 with 30 zeros next to it, a huge mass. We can see compared with the Earth's mass, which is 6 times 10 to the 24. So the sun is basically 6 orders of magnitude more massive than the Earth. If we look at the radius, the size of the sun, it's about 7 times 10 to the 5 kilograms compared with the Earth's, which is about 6.4 or 6,500 kilometers. If we took 109 Earths, we could fit them across the diameter of the sun. So that gives you a picture of how big the sun is relative to the Earth, more than 100 times wider or larger than the Earth. If we look at the energy output, we can measure energy in different units. So here it's given both in ergs per second, but also in watts, maybe something you're more familiar with a light bulb, which may be 100 watts at home or 50 watts. Here you can see that the output of energy is about 4 times 10 to the 26 watts, a huge amount of energy which is released from the sun. When we talk about the temperature of the sun, it actually depends where we're looking on the sun, but if we look at the inside part of the sun, it varies from the inside to the outside. It's about 10 million degrees. And we should point out that during the course we'll be talking mainly about Kelvin, the unit Kelvin for temperature, which is simply Celsius plus 273. So it's 0 degrees Celsius is 273 degrees Kelvin. The reason why we use the Kelvin scale is because we don't want zeros when we do our calculations. If you divide by 0, the calculations will explode. So absolute zero of 0 Kelvin is the coldest temperature you could get. It's basically when molecules and atoms stop moving, and then the scale continues positively up from there. If we use Fahrenheit or Celsius, it causes problem in science when we're trying to make calculations. At the surface of the sun, there's a different temperature, close to about 6,000 degrees, 5,900. It actually depends how we calculate the temperature, because nobody can actually go there and measure it. So we'll talk a little bit in this week of how we actually calculate and know what the temperature of the surface of the sun is. And that's compared to the Earth, which is around about 288, 287 degrees, about 14, 15 degrees Celsius. And the distance, how far away is the sun from the Earth? Well, this is about 150 million kilometers on average. We've already spoken before that in the paleoclimate section that the distance changes slightly throughout the year, but on average 150 million kilometers away we are from the sun. Now, it's estimated that the age of the solar system and the sun as well is about 4.5 billion years. And the energy that we get from the sun is basically produced by what we call fusion of hydrogen. Fusing is actually pushing physically the hydrogen atoms together. This needs a lot of energy, but when you have a huge amount of gravity at the center of the sun, you have enough force to fuse the molecules together, and this releases a huge amount of energy. That's the energy we get from the sun. And this process of fusing actually puts hydrogen atoms together and produces heavier elements like helium. And slowly with time, the core of the sun gets a larger mass because of this fusion process. So with time, we get an increase in the mass at the center of the sun. That means the gravitational force increases. When you have more gravity pulling the molecules together, you have more heating, and the sun actually becomes brighter. So over the lifetime of the sun, it's actually changed its brightness, and it's what we call luminosity and the amount of energy released from the sun. Now, our sun is very similar to all the other stars in the sky. Every star you see in the sky is a sun. It's just very far away from us, so it doesn't look very bright. And we know from looking at other stars in the sky and other solar systems very far away from us that there's this link between how bright the star is, we can see here on the y-axis, the luminosity, and its temperature, the surface temperature. And you can see the little star here on the graph, which is basically our sun. It's put it on the plot here on the luminosity. We've given the number 1, which means 100%. And you can see stars which are brighter, greater than 1, and those which are weaker, less than 1. And we also see that the temperature for our sun is approximately 6,000 degrees. So we know now from looking at many other stars in the solar system that our star is simply another star. Our sun is simply another star in the sky. It's very close to us, so we see it very bright in the sky, but it acts like all the other stars in the sky at night. Now, because of this increase in the luminosity, the brightness of the star over its lifetime, it's estimated that at the early sun, which we're talking about 4.5 billion years ago, when initially our star ignited and started to shine, it was much weaker than today. I just mentioned that it grows, the luminosity increases with time. And here on the plot we can see, say, over 4.5 billion years, based on different models of how the star actually decayed into its normal growth pattern. So these different dotted lines are just from models which show where the decay from the initial explosion and ignition of our sun to its normal burning and the fusion can be taking different times. But whatever model we use, we see that today, on this plot, if we look at today, basically 0 is today, and we're going back billions of years. Giga years are billions of years, so we can see here that the sun basically started burning about 4.5 billion years ago. The 1 on the y-axis represents, again, the amount of energy in percentages leaving the sun today, so this is 1 or 100%. And what we notice here is that if we go back 2, 3, 4 billion years, the sun was maybe only 80% of its energy that we see today, maybe even 70%, but a lot less than we have today. On the other hand, the Earth's climate has been quite stable over billions of years. And so this presents us a paradox we call the faint sun paradox, that the sun was much fainter in the past than it is today, yet the climate was more or less the same. So how could we have the same climate today over billions of years, but with a much weaker sun giving us much less energy? And if we look at this plot, this shows basically the paradox. So basically, this is a fairly complicated plot, but it shows what the change, first of all, in the luminosity of the sun, the brightness of the sun showing in the red curve. It shows basically the temperature of the Earth in the blue curves, one without an atmosphere and one with the atmosphere. And the light blue horizontal curve is basically the freezing temperature, where water will freeze. And what this says is that before 2, 3, 4 billion years ago, the temperatures of the Earth on average should have been below 0, and everything should have been frozen. And life shouldn't have formed on the planet Earth. On the other hand, if we look at all the geological evidence we have from fossils, in the ocean sediments, we see this area on the top here, this actual temperature of the Earth, this gray envelope, is what we can calculate from geological evidence that this is the temperature of the Earth over billions of years. So how could the temperature of the Earth be around about 15, 14 degrees, or maybe even a little higher, 20 degrees over billions of years when the sun was so weak? And if we were just relying on the sun, then we would have expected everything to be solid ice and no liquid water on the planet. So this is the basic paradox. And some people have tried to figure out how can we solve this, some solutions. So the first idea is maybe there was more carbon dioxide in the atmosphere. We know carbon dioxide is a very strong greenhouse gas. If we have a lot more carbon dioxide in the atmosphere, then we will trap in, even if we have less radiation coming in from the sun, we'll have a lot more being trapped inside, like putting blankets on the planet, and we would warm ourselves up, and we'd be able to be then above freezing. The drawbacks of this idea is that for this to happen, the Earth would have had to have maybe 1,000 times more carbon dioxide than we had in the pre-industrial era. And there's no evidence that this actually happened. The best estimates that scientists and researchers can make is that maybe in the early Earth we had maybe 40 times as much carbon dioxide in the atmosphere until photosynthesis started and then started to take out that carbon dioxide from the atmosphere. So in theory, this could work. In practice, we don't have any evidence that we had such high concentrations of carbon dioxide in the atmosphere. Another possible solution for this faint sun paradox is to have both more carbon dioxide and methane in the atmosphere. Now, methane is a much more powerful greenhouse gas than carbon dioxide, so we don't have to have too much more So combining both carbon dioxide and methane could possibly solve this paradox, allowing the Earth temperature to be above zero even though the sun is very weak. The drawback here too is that methane is normally produced by various microbes, biological activity on the Earth, and in the early Earth there wasn't any biological activity. And so it's difficult to explain how we would have had so much methane in the atmosphere before we start to see life developing on the planet Earth. And another problem is that when you have too much methane in the air, you actually produce a haze, a kind of a very thin cloudiness over the Earth, and this will reflect the sunlight and then cool it back again. So it won't actually warm the climate if you have too much methane in the atmosphere. A third option is that maybe there's more nitrogen. Most of the air here in the room and where you're sitting is nitrogen. And if we have more nitrogen, we actually increase the air pressure. By increasing the air pressure, we have more collisions between the greenhouse gases in the atmosphere, and this is a way that they can absorb more energy and warm up the atmosphere and prevent that energy releasing out to space. But again, when we look at the geological evidence about atmospheric pressure, there's very little evidence that it was much different than it is today, millions of years ago. And one other factor, if we have more nitrogen, nitrogen is one of the reasons we have the blue skies above our heads. We have what's called scattering of the radiation in different directions. The blue gets scattered the most, and some of that actually leaves the atmosphere. So if we have too much nitrogen, then we'll have more scattering, and this could also cool the planet, working against the warming effect. And the last possibility that people have proposed is to have more nitrogen and more hydrogen in the atmosphere. A higher concentration of nitrogen and hydrogen would allow, again, some formation of new molecules, hydrogen and nitrogen together, which act as greenhouse gases. And so these would also have a heat trapping effect to warm up the climate above the 0 degree level and allow liquid water on the planet. Again, there are drawbacks to this. Basically, there's no geochemical evidence from geology, from fossils, that the early Earth had a lot of hydrogen in the atmosphere. And if we did have a lot of hydrogen, it would have been consumed by the methane producing microbes on the Earth, and again then would have been reduced automatically by biological activity. So in conclusion, we still have this faint sun paradox. Nobody has solved this problem yet. They're theoretical ideas, but there's no scientific evidence to back them up. And so still today, there's plenty of room for you, the students, to do research, try to answer this question of how the Earth's climate has been constant over billions of years, while the sun has been much weaker in the past.